Hello, Roman, and welcome back to the series of the videos Neural Networks from Scratch in Go, where we dive into the bare bones of the neural networks using this book, but instead of the Python, we are writing everything in the Go lang. And the reason to this, because I want to make things more complex than just, copy pasting the code and trying to understand it. And usually I do understand things better when I'm trying to implement them. And yesterday I had a terrible headache. Seems that I'm feeling better today. So we can continue. And the last thing, like yesterday, I was studying, continuing the, chapter 4 activation functions, and I studied what is the Softmax, how it works, and right now I need to implement it. Where is it? Yeah, okay, so what is the Softmax activation and how it works? And we should have it as, where is it? We should have it as the second activation function for the output. But for now we need to, and that will be actually the end of the chapter 4. So for now, let's implement this. So we have our input as math_dense, which is the structure from the Go num, and we have rows as inputs, and in the columns we have the outputs from the previous layer. Well, the outputs from the layer, the layer that we want to apply the activation. All right, so the first thing, we're making the same size for the output. So we took the row and column from the input, and let's go next. So the first thing, I'm thinking I will create, probably I will create the function softmax, and it will take the float 64 as an input, and it will return float 64. And this will be the actual function that calculates on the row. And yeah. So I will try to implement the softmax function first, and then use it with the stuff from the Go num. So first thing, we need to allocate the output, and it will be float 64 by the len of the inputs, and we will return it. Next, I need to calculate the maximum, right? Wait, I actually need to calculate the max value. So we going to use max, and then for in range, no, confusing two languages, range input. By the way, can I use Probably there is a max function that slices, so max return the maximum value in X. This one, max return the maximum value in X. It panics if X is empty for floating point. So, and where is it? Slices sort. So it's slices sort. Max this one or this one? No, it's this one. Wait, max value max input. Okay, maybe it's sort max. No, max value declared but not used. Input. Could not import slice, no required. Okay, but oh, so it's slices. Okay. So we have slices and okay, we have the max value. Then we can we have the output, we have the X values, and for range X values, what we going to do? We need to take the math, I think X, right? And what we're taking the input and we subtracting the max value, right? So at this moment we should have this one covered. Okay, then we need to create the probabilities, but that will be actually the output. So for range output, no. We're taking the X value and oh, we need a sum, right? Sum. Do we have a sum? No. Sum returns, no, not this one. It turns a new string, but we don't have no. Hmm. Maybe like this. Oh. Oh, it's from go num. Okay, so we go num. What? X value is not used. Because that should be the output, right? Okay, so we make the output, we make the temporary array. We found the max value, then we exponentiate the input value that is minimized by the max value, and that is just to avoid overflow. Okay, and right, we should be able to use it. Okay, so I need to have a row. Not 3, it will be the C. Then copy. Then it's copy. Row view returns a slice backed by the same array as back in the receiver. So that will be my array, but how I can copy? Because I'm going to change it, right? But maybe I don't need. I mean, I created this, then what I can do, I can actually, maybe I don't need to create, wait. So I need to take the Softmax. I should be able to pass this, right? Okay, make it dense, copy, find, subtract, sum, normalize. Okay, we have a new row. Then we need to actually put it inside the output, right? Set set row, that is this one and this one. So that should be our... I'm not sure how, performance-wise it's okay. It doesn't look good, but right now, I'm not trying to implement the most efficient thing. But yeah, let's just take a look. So we're creating the output. Then we going through the rows. We taking the row. So that should return, that is backed by the same array as back in the receiver. So that will be, I guess, the reference, but we are not changing the inputs in any place. We're just reading from this and we making the new slice and we're returning the new slice. Actually, do we have delete? Do I have something like free? No. Okay. So we creating the output, creating the temporary one. Then we find the maximum value. Then we calculate the exponential values. Then we making a sum. Well, technically I can do it here, right? I don't have to go, but this is just small optimization, but for now I will leave it as it is. And then we calculate the output. So what does it mean? It means that we have our softmax, right? And we have the... Okay, let's take a look. We have the dense layer 1 activation, we have the dense layer 2, we have the forward, and okay, make a forward pass for the inputs, pass it to the activation. I have it right here. This is the real one. Then we make a forward pass for the second. So the second layer takes the activation 1. And right now we need to take the activation. So with soft max 1, and it will be activation, and soft max 1. And we take in the layer 2 output, and it means here we should have soft. That should work. Oh, okay. Okay, and I have actually more or less the same distribution, like here. We completed what we need for forward passing data through our model. We use the rectified linear activation function on the hidden layer, which works on a per neuron basis. Okay. We additionally use the softmax activation function for the output layer, since it accepts non-normalized values as input and outputs a probability distribution, which we're using as confidence scores for each class. Recall that although neurons are interconnected, they each have their respective weights and biases and not normalized with each other. As you can see, our example model is currently rendered. To remedy this, we need a way to calculate how run the neural network is at the current predictions and begin adjusting weights and biases to decrease error over time. Thus, our next step is to quantify how wrong the model is through what is defined as the loss function. So we're at the end of the, let me check the recording times, 20 minutes. Supplemental material, chapter code, further resources. Okay, I will take a look. Sample code. Okay. Okay, dense layer activation, Softmax. Yeah, it's all presented in the book. Okay. This one. Now let's go for the chapter 5. And I don't remember how many chapters are here, but it looks like I hit 100 pages out of 6.5. So let's go. With a randomly initialized model, or even a model initialized with more sophisticated approaches, our goal is to train or teach a model over time. To train a model, we tweak the weights and biases to improve the model's accuracy and confidence. To do this, we calculate how much error the model has. The loss function, also referred to as the cost function, is the algorithm that quantifies how wrong the model is. Loss is the measure of this metric. Since loss is the model's error, we ideally want it to be 0, but I'm not sure that it's possible to make the model that has 0 error, unless it's, I don't know, knows all the possible inputs and outputs, which is, not possible, I would say. You may wonder why we do not calculate the error of model based on the argmax accuracy. Recall our earlier example of the confidence, this one and this one. If the correct class were indeed the middle one, this one, the model accuracy would be identical between the two above. But are these two examples really as accurate as each other? Well, it's not. I mean, here, yes, this value is bigger than the second two. And it means that it has more confidence in the second class, but here the confidence itself is way bigger. They are not, because the accuracy is simply applying an argmax to the output to find the index of the biggest value. The output of the neural network is actually confidence, and more confidence in the correct answer is better. Because of this, we strive to increase correct confidence and decrease misplaced confidence. Categorical cross-entropy loss. If you're familiar with a linear regression, then you already know one of the loss functions used with the neural networks that do regressions: squared error or mean squared error with the neural networks. We are not performing regression in this example, we are classifying, so we need a different loss function. The model has a softmax activation function for the output layer, which means it's outputting a probability distribution. Yeah, probability distribution between 0 and 1. Categorical cross-entropy is explicitly used to compare a ground truth probability, y or targets, and some predicted distribution, y hat or predictions. So it makes sense to use cross-entropy here. It is also one of the most commonly used loss functions with the softmax activation on the output layer. The formula for calculating the categorical cross-entropy for y, actual divided by desired distribution, and, well, actual desired distribution and predicted distribution. Okay, so we But how do we know the desired distribution? I mean, we can know that there is we can know the concrete class, but how we would know the distribution for other classes? Okay, L denotes sample loss value. I in the is sample in the set. J is the label output index. Y denotes the target value and Y hat denotes the predicted values. Once we start coding this solution, we will simplify it further to minus logarithm from correct class confidence, the formula for which is minus logarithm of where yk is an index of true probability, where L from Y denotes sample loss value. I is the ith sample in the set, K is the index of target label, Y denotes the target values, and Y hat denotes the predicted values. Probably all. You might ask why we call this cross entropy and not log loss, which is also a type of the loss. If you don't know what log loss is, you may wonder why there is such a fancy looking formula for what looks to be a fairly basic description. In general, the log loss error function is what we apply to the output of a binary logistic regression model, which we'll describe in chapter 16. There are only two classes in the distribution, each of them applying to a single output, which is targeted as 0 or 1. In our case, we have a classification model that returns a probability distribution over all outputs. Cross entropy compares two probability distribution. In our case, we have the softmax output. Let's say it's this one. Which probability distribution do we intend to compare this to? Yes, we have 3 class confidence in the above input, and let's assume that the desired prediction is the first class. If that's the intended prediction, then the desired probability distribution. Okay, so it's that simple. And I guess over time, over changing the params, well, weights and bias of... Come on. And over time, over training, I think the goal of changing the weights and the biases is to shift this result for the specific input to be closer to this one, and I would get and the loss function will calculate, I think, how far you are from the ideal one. Cross entropy can also work on a probability distribution like this. They wouldn't have to look like this. On a probability distribution, they wouldn't have to look like one above. That said, the desired probabilities will consist of 1 in the desired class and 0 in the remaining undesired classes. Arrays of vectors like these are called one-hot, meaning one of the values is hot, turned on, which a value of 0, and the rest are cold, off, with the value of 0. When comparing the model's result to a one-hot vector using cross entropy, the other parts of the equation zero out, and the target probability log loss is multiplied by 1, making the cross entropy calculation relatively simple. This is also a special case for the cross entropy calculation called categorical cross entropy loss. to exemplify this, if we take a softmax output of this and target of this, we can apply the calculation as follows. Okay, so we have the target, we have the prediction, and we taking the negative number of the sum, we take the desired one, multiply by logarithm of the predicted probability, but then it's, well, basically it will be, you know, for the categorical tool, you will take the desired output, take the logarithm from it, multiply, well, not even the multiply, you just take the logarithm value from the probability and you make it negative, and that's it. So this is the error, right? Let's see the Python code for this. So we have the softmax output, we have the target output. Yeah, so we're taking the logarithm from the model's prediction, we multiply it by the target prediction, and we sum all of this, and in the end we receive the result. That's the full categorical cross-entropy calculation, but we can make a few assumptions given one hot target vector. First, what are the values for target 1 and the target 2? In this case, they are both 0, and anything multiplied by 0 is 0. Those we don't need to calculate these indexes. Next, what's the value for target 0? In this case, it's 1. So this can be emitted as any number multiplied by 1 remains the same. The same output then in this example can be calculated by just taking the negative logarithm from predicted probability for the concrete class, which gives the same. As you can see, with one hot vector targets or scalar values that represent them, we can make some simple assumptions and use a more basic calculation. What was once an involved formula reduces to the negative log of the class confidence score. The second formula presents at the beginning of the chapter. As we already discussed, the example confidence might look like this or like this. In both cases, the argmax of this vector will return the second class of the prediction, but the model's confidence about these predictions is high only for one of them. The categorical cross-entropy loss accounts for that and outputs a larger loss for the lower confidence. So I think for this one, right? So the more far away you from the predicting correctly, the bigger the value will be, well, without this sum. We have printed different log values for a few example confidences. When the confidence level equals to 1, meaning the model is 100% sure about its prediction, the lost value for this sample equals 0. The loss value raises with the confidence level approaching 0. You might also wonder why we did not print the result of log 0. We'll explain that shortly. So far we have applied logarithm to the softmax output, but have neither explained what log is nor why we use it. We'll save a discussion of why until the next chapter, which covers derivatives, gradients, and optimizations. Suffice it to say that the log function has some desirable properties. Log is a short form logarithm and is defined as a solution for the x term in an equation of the formula a in power of x equals b, So the x returns you the number of the power you need to use. Yeah. Well, I mean, it should be, yes, it usually should be written like this. But I guess by default, it's actually not log from 10. How it's properly called. I think it's ln that has the default base of 10. But somehow it... Oh yeah, it's actually logarithm with e as a base. Oh, from e. Okay. The natural logarithm, natural log, or simply log. You might also see this written as ln. Okay. So it's actually from e constant. I remember it incorrectly. Okay. But I remember that it exists. The variety of the conventions can make this confusing, so to simplify things, any mention of log will always be a natural logarithm through this book. The natural log represents the solution for x term in equation e in power of x equals b. For example, e in power of x equals 2.5 is solved by log. Okay. Yeah. We can confirm this by exponent changing our result. So yeah, basically we have a value. With the logarithm, we get the number of the power that you can use. And then you take in the e constant, making it in power of this value, and you get the same result. Well, yeah, the small difference in the result of floating point precision in Python. Getting back to the loss calculation, we need to modify our output in 2 additional ways. First, we'll update our process to work on batches of Softmax output distribution. But I think I already did, right? No? With the Softmax. Yeah. And second, make the negative log calculation dynamic to the target index. The target index has been hard-coded so far. Target index. Okay. Consider a scenario with a neural network that performs classification between 3 classes, and the neural network classifies in batches of 3. After running through the softmax activation with batch of 3 samples and 3 classes, the network output layer yields 3 by 3. We need a way to dynamically calculate. We need a way to dynamically calculate the categorical cross entropy, which we know is a negative log calculation, to determine which values in the softmax output to calculate the negative log from. We simply need to know our target values. In this example, there are 3 classes. Let's say we're trying to classify something as dog, cat, or human. A dog is a class 0, a cat is a class 1, and human is class 2. Let's assume the batch of 3 sample inputs to this neural network is being mapped to the target values of the dog, cat, and I guess human, right? So the targets as list of target indexes. Oh, no. Okay, so the first input of values will correspond with the dog, the second class targets. Okay, so instead, I mean, I guess it could, like 0, 1, 1. I think it could be like 0, 1, 1. So I would represent it like this, right? So you have the the one, like how it's called, turned on class, the zero class. Here we have the turned on first class, and again here. The first value is 0 in class targets, means the first softmax out distribution's intended prediction was the one at 0's index of. The model has a 70% confidence score that this observation is a dog. This continues through the batch where the intended target of the softmax is this one. The model only has a 50% confidence score that this is the cat. The model is less certain about this observation, and the third one, it has the higher confidence value of 90%. With the collection of the softmax outputs and their intended targets, we can map these indexes to retrieve the value from the softmax distribution. Class targets, softmax outputs. So okay, we took okay, so here we have the 3 by 3, where the 3 is the batch, and here we have these 3 values, 1 value for each batch. So for example, the first input, once it went through the neural network, it ended up after the softmax output with 3 probabilities, and the loss function will calculate the difference between the this probability and the desired, which should be the 1. So it will calculate, I guess, the difference between this one and 1, then this one and 1, and this one and 1 again, and then calculate the loss, right? The zip function again lets us iterate over multiple iterables at the same time in pattern. This can be further simplified using NumPy. Well, we'll have to do it in a different way. Okay, so we get this. Actually, yeah. What are the one So for the first row, let's take the, well, for the 0 row, let's take the 0 index. For the first row, let's take the first index. For the second row, let's take the first index. I think it will be like this, right? This returns a list of confidence at the target indices for each of the sample. Now we can apply the negative log. Range creates an array from 0 to len -1. So it will be like this. Then it takes the class target, so the class target array should have the same length as the rows number in the softmax output. So then it will return the, well, return the value, and then it will, yeah, calculate the logarithm value for each one. finally, we want an average loss per batch to have an idea about how our model is doing during the training. There are many ways to calculate an average in Python. The most basic form of an average is arithmetic mean, and is sum of iterable divided by the length of the iterable. Well, arithmetic mean, you sum all of the values and you divide by number of the values. NumPy has a method that computes this average on arrays, so we will be using that instead. We add NumPy's average to the code. Okay, so, and this is the average loss for the whole batch. Right? We have already learned that targets can be one-hot encoded, where all values except one are zeros, and the correct label's position is filled with 1. They can also be sparse, which means that the numbers they contain are the correct class numbers. We're generating them this way with the spiral data. Oh, okay, this is why I need it. Function, and we can allow the loss. Well, actually, I realized that that should be like this. Because the spiral data returns 100 samples for one class and I have 3, so it will return it will return 300 values of data, right? And inside there will be 2 values for x and y. Yeah, so this is why we have 3 by 2. Yeah, that's actually more correct. And here we will have classes. It's not used for now, but that will be an array of classes that will contain, I think, 300 of the elements, right? Yes, samples multiplied by classes, right? And that will be, you know, for every output. So right now it has the probability of the 3 classes. So for example, for the last input, it calculated the probability of 33% for each class, but the last one actually, I think that will be the last class. So that value should be increased and those decreased. The check can be performed by counting the dimension. It targets a single dimension like a list. They are spare, but there are 2 dimensions like a list, and there is a set of the Softmax output, which is also an input to this loss function, consists of numbers in the range from 0 to 1. A list of confidence. It is possible that the model will have full confidence for one label, making all the remaining confidence zeros. Similarly, it is also possible that the model will assign full confidence to a value that wasn't the target. If we then try to calculate the loss of this for confidence of 0, yeah, you cannot. Before I explain this, we need to talk about the logarithm. But okay, I think this is the good time to stop. Tomorrow I will start from what the logarithm is, I think, and then I see that we're going to create the loss class that will calculate the categorical loss, I think. Calculate sample losses. Oh yeah, loss categorical cross entropy loss. And yeah, this is what we're going to implement. Then we will combine everything together. I think this is activation, yeah. Then we'll calculate the loss of the... and then we'll see the value. And then accuracy calculation, and that's it. So I think we should cover this implementation of the loss and the accuracy tomorrow, right? And then we'll go for the next chapter. But for now, thank you for watching, and I see you tomorrow. Bye-bye.